Hi, I'm Xiaohua Xu from UT Austin. Sorry that I have to make this lecture in this format. Over this part of the lecture, I'll make a brief introduction to the GMTSAR software. So we'll go over some of the designs of the GMTSAR software, update you guys with some of the newer features or recent developments, and I'll talk a bit more on the newer missions, relatively newer missions. So GMTSAR is a open source INSAR processing software. It has the capabilities of handling most of the open SAR data, from processing a pair or interferogram to doing a large stack of data using GNU parallel. It has tools to do time series with atmospheric corrections as well. And most importantly, it is completely free and open. That means anyone could take any piece of the software for commercial or personal use. You can copy it, modify it, redistribute it without any restrictions. The software is written in C, most of the modules for the processing modules, and C shell to connect them together. There will be a Python version in the future, which kind of depends on our founding status, but that's one of the future directions for sure. The product of GMTSAR is fully compatible with GMT. If you want to use the result to produce publication quality figures, which makes things easy to handle if you are familiar with GMT. GMT is, by the way, is generic mapping tools, which is a popular software for plotting earth science data over maps. If you are an advanced user, you could easily manipulate the product from GMTSAR using the functions in GMT. And lastly, we try our best to make the processing chain really simple and easy to modify so that you can basically build your own processing chain or implement anything that you want to replace part of the GMTSAR processing. Okay, here's a diagram of the design of GMTSAR. The entire processing chain is divided into 6 steps, and we are gonna go over them one by one. The first step is called pre-processing. The objective of this step is to convert the incoming data from different space agencies into a format that can be recognized by the GMTSAR software. This is a part where the software differs the most from one satellite to another. If every agency could agree on a common format, everything would be much easier. But it's hard to see that happen. Anyways, this step usually converts the satellite data into 3 files. A data file with the suffix of .raw or .slc, which stands for single log complex. Basically, they are just a big chunk of binary numbers. And also another file is a parameter file with the suffix .prm, which stores all the metadata that will be used for processing the data. And an orbit file with the suffix .led, which is the needed orbit records to calculate and interpolate the orbit. The associated modules that are usually used are often given the name like ERS preproc or NV preproc, and so on. And after you get these kind of files that can be recognized by GMTSAR, the second step is to focus the image and perform characterization, which is also called alignment. Focusing is a step to convert the raw data or raw radar echoes into the single log complex images. Basically, after that, you can consider the measurement to be from a very, very long antenna that has pretty good resolution along the track direction. Nowadays, many satellite agencies has taken this part as their job. So the data you get normally are already in the SLC format, like Sentinel-1 and ALOS-2. Then after you have this format, then you have to perform the alignment step, or called characterization, which is basically matching the 2 images together so as to make sure they are mirroring the same thing from pixel to pixel. The reason that you have to make this step is because every time the satellite makes an acquisition on the ground, the footprint is not always perfectly aligned together. So you have to like make some adjustment to stretch it or shift it a little bit to make them match. The third step is called back geocoding. It is a step to project the topographic information into radar coordinates. So later on, when you are doing interferometry, the topographic phase could be corrected. Sometimes this could be quite slow, depending on the interpolation approach or how large of an area you are performing this back geocoding. The one module that is called here is called DEM to topo RA.CSH. Then you have everything ready to do interferometry, which is basically differentiating the radar phase of the two images. And also filtering is also done for this fourth step as well. The theory of this part will be covered like later on, so I'm not going to talk too much on it. And once you have the radar phase, you could unwrap them. Phase unwrapping is basically to connect the radar fringes into a continuous phase map. This is kind of necessary if you want to measure deformation. It is more like an art sometimes, and this part will be covered tomorrow. Lastly, you could geocode your product. The information used for geocoding is actually from this step 3. Back geocoding. Basically, we produce a large lookup table used to interpolate the data from radar coordinates to geo coordinates. The main script used here is actually called proj RA, which is radar coordinates, to LL, which is long lat. Or you could use the higher level script called geocode.csh. Okay, some more stuff. Other than the processing chain itself, we have some modules or scripts outside of the standard processing chain, like we have modules to do corrections like tide correction. You can estimate allosteric phase. We do also have time series tools, which is based on, which is using a coherence-based SBAS. SBAS is a time series approach, by the way. And also we have some data manipulation tools where you can cut, paste, or like reassemble data, or like we call them bursts. Many of them are for Sentinel-1 though. And lastly, we have this, we call them top level scripts, which are used mostly by users, I think. They basically cause the modules mentioned above to finish the processing chain. If you have tried some of the example data sets on the Topex side, you probably notice that this P2P processing.csh, that script, is in almost every one of them. We do have some other top level scripts to deal with frame-wise processing. For example, for tops, you have Sentinel-1, you have P2P S1 tops frame. And for ALOS2 ScanSAR, you have this ScanSAR frame script. For dealing with large stack of data, there are also some batch scripts. They are written for, I think, tops, ALOS2, and some of them are for even earlier data sets like ERS. But later on, we're actually thinking of writing newer batch scripts by purely calling this P2P processing script, because now it has the capability of dealing with individual steps in the processing chain and basically apply it to different data sets by manipulating the config file. This is sort of the design that we want users to do later on. So this is actually the core script right now. I also want to update you guys with some of the recent progress of GMTSAR. Most of them are from the past year or past a few years. I want to mention some of them here. We do have an allosteric correction module in the script now, but mostly they are tested for Sentinel-1 and ALOS2. We now have a new SBAS parallel module that is enabled with OpenMP, so you can actually speed up the time series analysis part. And to reduce the memory cost for that SBAS program, we also built in an mmap option. So it'll swap disk space for use of memory. Now we also have modules to do geocoded SLC, and we added a bunch of scripts to do INSAR GMSS integration as well. We also added a phase gradient option, so now anyone could just turn it on and get phase gradient estimates. It is useful for detecting very small changes. We added more preprocessors like for GF3 data, and also automated orbit downloading script is also available. We also added a new interpolation approach for doing back geocoding. This is fast, but requires GMT 6.4, and it's not fully tested with time series yet. we do welcome feedback, so of course. I guess the overall idea for this slide is that we want to let you know that we are actively developing this software, and any kind of help is really appreciated because we are kind of a small team. And if you want to contribute, don't hesitate to open an issue page on the GitHub to like request a new feature, report a problem, or help us build a new feature into the distribution. Here are some examples of the ionosphere correction module in GMTSAR. They are for ALOS-1 on the top right over here, and ALOS-2 and Sentinel-1. These are example data sets on the TOPEC side. Feel free to play with them. But I do want to warn you guys that this filtering part of the ionosphere phase estimate is kind of slow. That might be probably going to be our next target to make it run faster. Okay, I want to talk a little bit more on the new missions or newer missions. So ALOS-2 is an L-band mission from the Japanese Aerospace and Exploration Agency. It has a 14-day possible repeat, but normally you get less acquisitions than that. Like here at San Andreas, in California, you get basically 42-day repeat, and they're in GMTSAR mode. The data is free, but you have to write proposals to get it. And they mentioned that they are going to open their data, and hopefully that's going to happen soon. Sentinel-1 is a C-band twin satellite system that has 6-day repeat possible, I think. Most of its acquisitions are in this TOPS mode. We're going to cover that later on. The data are completely open and free. Also, ASF, which is Alaska Satellite Facility, has these data archived. So if you're going to download that data from North America or South America, that might be a faster route. And unfortunately, Sentinel-1B died last Christmas, but I guess Sentinel-1C is going to get launched. So we're still going to in this twin satellite system. Both satellites have really good orbit control. They have their advantages and disadvantages. Currently, they are the free SAR data that's used a lot in the Earth science communities. In less than 2 years, there will be another new SAR mission, and it's free. Its data is free. It's a NISAR mission. I think I've been saying this for like 3 consecutive years now because of the launch dates keep getting delayed, mainly due to COVID. But NISAR should be a new game changer as it has ionosphere correction designed from the beginning. And the data volume you're going to get each day is around 80 terabytes. That's like tons of data. Right now, till like maybe a few years later, is probably the best time for INSAR. And I want to show that with this diagram, which is the number of maximum acquisitions you can get every year for an area that's under the observation plan. In the 90s, you could only get ERS data. That's when David started to work with INSAR. I myself started a little bit late during a time that when NVSAT and ALOS-1 are dead, where ALOS-2 and Sentinel-1 hasn't got launched. So my first PhD project was to dig into the earlier data sets. Now, if you guys join right now, you are basically at the historic high. It's probably the best time for SAR. I'm going to stop here and take questions. Thank you.